So outside is vertical, inside is horizontal. So let's go through the rules of transformation and the general rules, and then we'll get into some examples of different ones. So if you have a function and you add something on the outside, that is going to move it up k units. That is a transformation moving the picture up, ever how much you add. Okay. So if we had originally the absolute value function and we just put like a +5 outside of it, it would take that v and just scoot it up 5. That's the transformation that's happening. Okay. Guess what happens if you subtract on the outside? Yeah. Down k units. That's pretty easy, right? We can do that. Now, notice where the adding and subtracting is. It's on the outside of the function. The next one, if I add on the inside, that's going to move me left k units. If I subtract on the inside, that's going to move me right k units. By the inside, I mean on an absolute value, it'd be in between the bars. On a square root, it'd be inside the square root symbol. Okay. On a quadratic, it'd be inside the parentheses. We'll see some examples of this in a minute. Okay. So these transformations are up, down, left, and right. That's not changing the size of the graph or anything. It's just changing where it's at. It's a location changer. Okay. The next thing, what if you multiply the function on the outside? So I'm multiplying some number a, doesn't matter what, it's a times whatever function. If a is greater than 1, that is a vertical stretch. A vertical stretch. Multiplying on the outside of the function. So that's like a 3 in front of the absolute value bars. If a is between 0 and 1, that is a vertical compression. You may also find that said as a shrink. What kind of numbers are between 0 and 1? Decimals, fractions that are smaller than 1, like proper fractions like 1/3, 2/5, something like that. Decimals like 0.7, 0.3. Those are numbers that are between 0 and 1. Notice that multiplier is on the outside. It's a vertical move. Y'all ever play with silly putty? I got boys at home. We still own silly putty. And I still like playing with it. It's fun. We used to have the old brown looking silly putty, and we used to get these things delivered to our house every day. They were called newspapers. You don't get those anymore. But we used to get one every day. Jackson's son came to my house every day. And I always would either go get, when I got older, the sports section was the only part I wanted to read. But when I was younger, it was the comics. I'd go and I'd get the comic section, and then I'd be sitting around and had nothing else to do. We didn't have iPhones or anything cool like that growing up. We actually had to entertain ourselves. And I'd take a silly putty and I would press it out flat, and then I'd put it on a picture of Garfield. Press it down on the paper, and then when you peeled it up, what happened to it? Y'all remember? The ink transferred to the silly putty. You had the picture of Garfield on your silly putty there. And a vertical stretch is like you took that silly putty and you pulled it like this. And Garfield went from being this round, fat little cat, when you pulled it like this and it stretched it, made it skinnier. That's what happens to the graph of the parent function when you have a multiplier out front that's a bigger number than 1. If you have a 2 out there, it's going to make it skinny. If you have a 5 out there, it's going to make it really skinny. Okay? If you have a fraction in there, it's like taking Garfield and squishing him down. And what's going to happen when you squish him down? It'll spread out, right? So the graph, if it's a V shape and you've got a small fraction in the front, like 2/3, it's going to spread out and it's going to look wider. Okay? So that's what the vertical stretch and compression does. So that number is that. Okay? Now, if you put the multiplier on the inside, I'm going to use a different letter just so we don't get confused. I'm going to use a B. If B is greater than 1, that's going to be a horizontal compression. If you compress something horizontally, if I take my water bottle and I compress it horizontally, what happens to it? It gets skinnier, right? So horizontal compression makes it skinnier. If the multiplier on the inside of the function is between 0 and 1, that is a horizontal. Spell horizontal. Horizontal stretch. That's going to spread it out. So the thing that comes into play here is if you rely on the graph only and not the equation, a horizontal compression and a vertical stretch look like the same thing on a graph. But the equation is much different because of where the multiplier is. Okay? So if it's a vertical stretch, the multiplier is on the outside. If it's a horizontal compression, it's still going to make it skinnier, but it's on the inside of the equation, not the outside. A horizontal stretch is going to make it wider. So is a vertical compression. But it's where the multiplier is in the equation that helps us decide which one it is. Because if we graph it with our calculator, that's fine, but we're not going to be able to tell the difference in the look of it. Okay? So if you had that wad of silly putty and I stretched it this way, it's going to get longer, right? It would also get longer if I took that wad of silly putty and pressed it this way. If you came in and looked at the silly putty, you thought it was supposed to be in a ball and it was longer, and you didn't see me do that, you don't know which one I did, right? It would be hard to tell by just looking at the graph. That's the way we gotta learn this in this section is based on the graph. Okay. Next transformation is reflections. So if you have a negative on the outside of the function, that is a reflection over the x-axis. If you flip something like this line, this ruler is the x-axis. If it's up here to begin with, above it, and you reflect it across the x-axis, it flips it down here. That's a vertical move. Look where the negative is at. It's on the outside of the function. That's a vertical move. Flipping across the x-axis or reflecting across the x-axis is a vertical move. If the negative is on the inside, you're going to reflect a reflection over the y-axis. Y-axis is up and down. If you move across it, that's a left to right move, reflecting across the y-axis. The negative is on the inside of the function. Okay. All right. Outside is vertical, inside is horizontal. That's going to help us. Have that little set of rules there. That I've got a PDF that I meant to print for you, and I tried to print to the printer up here, and it wouldn't let me. So I got to get Mr. Youngerman to help me with that sometime. But I'll share that PDF that has these same rules in probably a little bit better organized thought process with you in the announcement this week. But writing them down helps us remember them better, I think. Okay, so what we're going to do is we're going to look at some equations and determine what transformations are happening. Okay, so we're going to describe the transformations. So this is not, I'd say this is probably not the hardest thing we've done. Let's start with the parent function. F of x is equal to the absolute value of x. We'll start with that one. Example A. Here is the transformed function. Absolute value of x minus 3 plus 5. This one has two transformations that happen to it. What are they based on the rules that we just went over? What does this plus 5 on the outside do to the V shape that the absolute value graph is originally? Up 5. The other one is the minus 3 on the inside. What does it do? Nope. On the inside. Go back up there to your minus on the inside.
Move it right 3 units.
Right 3 units. Up 5, right 3. That's what it does. What you can visualize happening is that V shape, instead of being at the origin, it's going to move it to the right 3. So we're going to go 3 to the right and then 5 up. So that's going to put me up in the first quadrant with that V, which would change my range. My domain's still going to be the same. My range will change. The idea is visualizing these transformations based on the equation. Let's do another one. Same parent function, different transformations. 3 absolute value of x plus 1 minus 4. So this one has 3 transformations done to it. So let's get the ones that we already know about or we kind of did in example A. What's the minus 4 on the outside do? That's a down 4. What does the plus 1 on the inside do? Left 1. Now we got this multiplier that's on the outside. So if we multiply by something bigger than 1 on the outside, go back to my rules, something bigger than 1 on the outside, vertical stretch. That's not too bad, right? That's pretty easy to do. Here's the cool thing. Those rules are the same if I change the parent function. Let's make our parent function f of x is equal to x squared. And example C is f of x equals parentheses 1/3 x squared minus 2. So what transformations happened there? Okay. The minus 2 on the outside is the down 2. That's good. Now this weird one, we hadn't seen this one yet. The multipliers on the inside of the grouping symbol or inside of the function. Horizontal compression or stretch? Why is it a stretch and not a compression? It's between 0 and 1. It's a small fraction. So that's why it's a horizontal stretch. Horizontal stretch. Let's do another one. Let's say we had f of x equals negative 1/2 x minus 5 squared plus 10. This one has 1, 2, 3, 4 things happening to it.
Positive 10 is up 10.
The positive 10 is up 10. I'm with you there. Good. Right 5. Good. Picking off the easy ones. Vertical compression, that's the 1/2 there. Reflection over the x-axis. Where'd that come from? The negative. That negative in the front there is where my reflection over the x-axis came from. So what I can visualize is the parabola, so that U shape that we've seen, moving it to the up 10 and then to the right 5, and then vertical compression is going to make it wider, and then it flips over the x-axis. You can see that we can maybe visualize those things happening. You can graph that equation with your calculator, but it's hard to tell the difference in a vertical compression and a horizontal stretch on the graph. So like, I'm going to graph that just to show you. So I've got negative 1/2, so the fraction alpha y equals 1/2 parentheses x minus 5 close parentheses squared plus 10. I'm going to have to adjust my window a little bit probably. It worked out all right. So there's the parabola shape. It's right 5, up 10, flip it over the x-axis. Hard to tell if it's wider or not by just looking at that graph. But by looking at the equation, I can tell that it's a vertical compression, and it pushed it down and made it wider. If I graph the original x squared, you can tell that the blue one's a little bit wider. It's not much wider, but it's a little bit wider than that. So that's that vertical compression happening. All right, what if the parent function is f of x is equal to the square root of x? Here's our transformations. Negative square root of x plus 2, and then a plus 8 on the outside. Up 8. Yep. That negative reflect over the x-axis. Good. Yeah. The plus 2 on the inside is going to be left 2. The rules don't change even though the parent function changed. Those rules are the same rules no matter what kind of function we're dealing with. When we get into Math 110 and we're dealing with different functions than these, same rules. We already know them. They're the same. They work for every type of function. Those same rules do. Let's do one more. F of x is equal to 7/5 negative x. That's instead of parentheses, that should be a square root symbol, sorry. Negative x plus 18 minus 1.
I meant down 1, sorry.
Down 1. Good.
Left 18.
Left 18. Yeah, that negative right there in the inside there is reflect over the y-axis. And then one more thing. That guy right there, what's he do? Mm-mm. I agree with vertical. Why is it a stretch and not a compression? 7/5 is how much compared to 1? It's more than 1. So that's why it's a stretch and not a compression. 7/5, it's a fraction, but it's a larger fraction. It's an improper fraction. So it's bigger than 1. Okay? All right. Next thing is symmetry. That we're going to talk about a test that does symmetry. We got 1, 2, 3 more examples. Got a couple of rules to write down, but we only got 3 more examples. We're almost out of here. I know you are tired. I'm tired too. So, symmetry. What is symmetry in math? What's symmetry at all? Go ahead. Mirroring, yeah, it matches up, right? So if I think about this smouse pad here. If I folded that right across the middle, it's symmetric. It matches up like that, right? So the shape matches up. That's what symmetry is. So symmetry is can be with respect to the y-axis. We plug in a negative x to the function. If everything simplifies to be equal to the original function, then the function is symmetric with respect to the y-axis. So that's one type of symmetry. Okay. The notation for that is f of negative x is equal to f of x. When we put in a negative x and simplify it, it turns back into the original function. We work it out a little bit. Okay. Symmetry with respect to the x-axis. Symmetry with respect to the x-axis, you set the function equal to negative y and solve for y again. If the function is the same as the original, then it is symmetric with respect to the x-axis. That would mean you could fold it on the x-axis and it match up. Symmetry with respect to the y-axis means you could fold the y-axis and it would match up. Symmetry with respect to the x-axis means you could fold it on the x-axis and it match up. Okay, so we can use the graph to help us with this, but we can do this algebraic test. So let's do an algebraic test real quick. So determine the symmetry for f of x. I think this is example G, maybe? Is that right? Yes, it is. Yay. F of x equals x squared plus 4. Okay. So we're going to test for y-axis symmetry. That's the first thing I'm going to do. I'm going to plug in a negative x. What happens when you square negative x? What's negative x times negative x? Positive x squared. Is that the same as the original? Yes. So this is the same. So it is symmetric with respect to the y-axis. Let's look at the graph and show you what that means. Okay. So on my calculator, I'm going to hit y equals. I'm going to clear out the stuff. I'm going to put in x squared plus 4 and just graph it. Visually in your mind, if you folded that along the y-axis, it matches up, right? We could see that if I were to pick up that screen and fold it along the y-axis, it's symmetric. It matches up perfectly. Okay. Now, can you look at that and tell me if it's symmetric with respect to the x-axis? It is not. Let's show that. I'm going to show you that algebraically that it is not. So algebraically, so this is the test for x-axis symmetry. So negative y is equal to x squared plus 4. If I try to get y by itself here, I'm going to divide by negative 1. What happens to those? They all change signs. Is that the same? Completely the opposite. Not symmetric. Not symmetric. Not symmetry. With respect to the x-axis. Now, here's a neat thing that is also possible. Symmetry with respect to the origin. Fold on y-axis, then x-axis, and matches up. Algebraically, that's a little harder to do. We're going to learn something else in just a second that makes that a little easier. Okay? So you have symmetry with respect to that y-axis. When you plug in a negative x, you get the same function back. Symmetry with respect to the x-axis, you set it equal to negative y and solve for y. Just divide by negative 1. If the negatives all cancel back out, it's symmetric with respect to the x-axis. That doesn't happen very often. Symmetry with respect to the origin isn't y-axis and x-axis. It's folded on the y-axis and then folded again on the x-axis, and it match up. So you folks that are a little more artistic and visual learners can probably visualize that a little bit better than some of us other folks that are not as much that. Now, here's the neat thing that comes along with this, and that is the odd, even, and neither. And this is the last thing of the lesson, okay? It's odd, even, and neither tests for functions. So functions can be odd, even, or neither, just like numbers can. We have odd numbers, we have even numbers, we have zero that's not odd or even. Okay? So functions can be those things too. Odd functions, if I plug in a negative x and I get back the opposite, the opposite signs on everything in the problem, it's odd. Even functions, if you think about, I think about my dad when I think about even things, because he's pretty even keel, is the way that they'd always say it. Doesn't really seem to matter what happens to him. He always has basically the same demeanor all the time. That's just who he is. Has been for 43 years. Doesn't mean he didn't get mad, but he's pretty even when it comes to things. Nothing, not extreme one way or another. He's pretty even. So even functions, when you plug in that negative x, something negative happens, you just come back to normal. So that same test for symmetry with respect to the y-axis, the same test for even. So if you get even, you get y-axis symmetry. If you get y-axis symmetry, you get even. They're the same. Same test. Okay? Let's look at that. Anything else, it's neither. So let's look at a couple examples of that, or a few examples of that. So here's example H. F of x, 8x to the fourth minus 3x squared. Is this odd, even, or neither? How do you know? I'm going to plug in a negative x. This is the way I can know. If I plug in a negative x, what happens when I say negative x to the fourth power? It turns into x to the fourth. That's 8x to the fourth. What happens when I square negative x?
X squared.
It's x squared. So that's negative 3x squared. What do you notice about that? It's the same. So that means it's even, because they're the same. That's how you can know. Plugged in the negative x, simplified. So when negative x times negative x times negative x times negative x, that's x to the fourth power. Two negatives make a positive. Positive times positive is positive x to the fourth. Multiplied times 8 is 8x to the fourth. Negative x squared is negative x times negative x. That's positive x squared times 3 is 3x squared. That's exactly the same as what I started with. That's why it's even. Let's do another one. Let's say we had 3x to the fourth minus 5x. I'm going to plug in the negative x, and that's going to tell me whether it's odd, even, or neither. What happens to the first piece? It stays the same because negative x to the fourth power, we've already talked about that. That's x to the fourth. So that's 3x to the fourth. So far it's the same. So that changes to positive 5x. Is it odd? It's neither because everybody didn't change. To be odd, everybody has to change. Only part of you changed here. So that's a neither or neither, depending on, I don't know where you're from. So if you're from McNairy County, it's neither. A lot of functions are neither. A lot of functions are odd. A lot of functions are even. No, not really a. One more. F of x, 6x cubed minus 9x. Odd, even, or neither, and why? Plug in a negative x, and then we're going to simplify.
Negative 6x to the third
Negative 6x to the third
plus 9x.
plus 9x.
So it's odd because both changed.
Everybody changed, so that's odd. That's correct. Because everybody changed signs. Plug in a negative x. Odd, everybody changes. It's the opposite. Even, nobody changed. Something negative happened, you still had the same demeanor. That's how I remember it. Okay. All right, I'm going to write down the suggested problems, and if anybody wants to stay and do another domain red flags problem, you can. If you want to go, you can go. But the suggested problems from the textbook, if you want to do some of those, 1 through 85, odds, obviously. And I'm not saying do all of those, but 2.6, 1 through 17. Not many questions on the middle section there. And then 2.7, 1 through 93 odd. So we did a whole section there, 2.3 and 2.7. Okay, so if you want to go, you can. If you want to stay and do another domain problem with me, you can. Oh, thank you. If you borrowed a calculator, just lay it on the front desk here on your way out there.
So I have like a Chromebook or anything. I have a MacBook,
Mhm.
and the main reason why all the quizzes, the ones that I got wrong, like it would have, it wouldn't like have
You got to use the Chrome web browser. You got to have the Chrome web
the
browser.
Chrome with that.
Yeah, that's what you, and you can download that from Mac. Just download the app. It'll fix that issue.
Okay, because I think that's why I got most wrong.
If it didn't show you the answer, yeah, it should have.
It didn't show me the problem or the answer. It
Yeah,
showed
should have
the
emailed me.
question.
I can tell you that. Yeah, it's just the Chrome web browser will fix that issue. Yeah, use the Chrome web browser and that'll fix all that.
I'm still getting my calculator in the mail for the next test. You said we'd be using them.
Mm-hmm.
Can I borrow one if that's okay?
I'll do it next week, and that'll be the last week I can. It should be in by I mean, this is the third week of the semester, so
I'm trying to order mine, and it's taking forever. So I was
it
wondering.
shouldn't take more than 3 weeks. I promise you that. But I'll let you borrow it for the test on Monday.
Thank you.
The first lab, was there a back? I didn't know that.
When is their test?
Next week.
Okay, I am so.
All right. Did you get on Canvas and you did the quizzes from the first week and watched the video and all
Did
that
a
stuff?
couple, yeah. I watched the video.
Okay, all right. So that
I'm gonna have to do it again.
Yeah.
I mean, it's been 10 years since I've been in
Oh,
a class.
it's tough. It's tough. I'll send a review
Okay.
tomorrow for the
I'm
test
gonna go through it again.
and go through the review. And if there's questions you have from the review, email me which problems you had trouble with, and I'll try to send something back to you that's hey, this is how you would work that problem.
Okay, and can you get those calculators out like Walmart?
Yeah, Walmart carries them.
Okay.
Yeah, absolutely.
And right after I bought mine, I went to Walmart and I'm on cash for $80.
Yeah, you might catch it on sale right now because it's after the first of school. They've got to run out of them. Yeah. Hey, Miss.
Crashed my lap.
Well, it'll be okay.
Look.
Don't worry about it.
Okay. I says, I'm looking at this. It's pretty. I'm thinking about my red baby cigarette.
It's okay. It's okay. We'll get you